All right, let's just jump right in with maybe the biggest question there is. What is everything actually made of? We're about to go on a journey that's going to take us from something you can see in your own living room all the way down to the truly bizarre rules that run the entire universe. You know, this whole thing doesn't kick off in some fancy high-tech lab. Nope. It starts with something you've probably seen a million times and maybe never really thought about. It's this little clue that's been hiding right under our noses for forever. Picture this, right? A dark room, and you've got that one single beam of sunlight cutting through the air. And what do you see? You see these little specks of dust just dancing. They're swirling and jiggling around like they're alive. But of course they're not. So what in the world is making them move? Believe it or not, that little random dance is the first clue. It's the first breadcrumb on a trail that's going to lead us right past one of Albert Einstein's most brilliant moments and drop us smack in the middle of the weird, wonderful, and frankly, mind-bending world of quantum mechanics. So first, let's rewind the clock. We're going all the way back to 1827. There's this botanist, Robert Brown, and he's just looking at some pollen grains in water under his microscope. And he sees the exact same thing we see with the dust in the sunbeam. These tiny little grains are just moving around all over the place, totally randomly, and they never stop. What he'd stumbled upon is something we now call Brownian motion. And here's the kicker. What's actually going on is that the pollen, or the dust, isn't moving by itself at all. It's being absolutely hammered from all sides by trillions, and I mean trillions, of invisible particles. Think of it like a giant game of cosmic pinball, where the dust speck is the ball. And that right there, that's a huge deal. It's one of the foundations of modern chemistry and physics. The fact that you can see this big piece of dust jiggling around is real, actual proof of an invisible, super hyperactive world of atoms and molecules. And it leads us to this really powerful idea, the particle theory of matter. And honestly, it's a pretty simple but incredibly powerful set of rules. It basically says, 1, everything is made of these tiny particles. 2, these particles are always moving, constantly jiggling around. 3, they kind of stick together. They attract each other. 4, there are tiny little gaps between them. And 5, when something gets hotter, it just means its particles are moving faster. That's it. And with just that, you can explain, well, pretty much everything you see in your everyday life. And this is a great way to picture it. Think about a solid, like ice. The particles are all locked up tight in a grid, just kind of vibrating in place. Then you add some heat, they get more energy, and it becomes a liquid. Now they can slide past each other. Add even more energy, and boom, you've got a gas. The particles are just flying around, totally free, bouncing off everything. It's the same exact particles, right? Just with different amounts of energy. Okay, so for a long, long time, this particle theory was just that, a really good theory. It made a ton of sense, but proving it, that was a whole other problem. I mean, how do you prove something exists when it's way, way too small to ever see? Well, it turns out it took the genius of a young Albert Einstein to finally nail it down. So in 1905, which, by the way, was his miracle year, he published a bunch of groundbreaking stuff. Einstein drops this paper on Brownian motion. But he didn't just describe what was happening. No, he did something much more clever. He built a mathematical model that made a very specific, very testable prediction. And this is where the pure genius comes in. His math predicted exactly how far a tiny speck of dust should move around based on how many invisible water molecules were smacking into it. And when other scientists went and did the experiments, the numbers matched. They matched perfectly. Just like that, Einstein had proven atoms were real, without ever seeing a single one. It's just incredible. All right, so atoms are real. Einstein proved it. Case closed, right? Well, not quite, because that incredible discovery just opens up a brand new rabbit hole, a deeper question. What are the atoms themselves made of? I mean, we all learned about protons, neutrons, and electrons, but can we go deeper still? Oh, yes, we can. Welcome to what you might call the universe's fundamental recipe. This right here is the standard model of particle physics. Now I know, it looks super complicated, but the core idea is actually pretty simple. Every single particle on this chart is what we call fundamental, meaning you can't break it down any further. This is it. This is the ultimate ingredient list for you, me, the stars, literally everything. The easiest way to think about it is to break it down into 3 basic groups. First up, you've got the quarks. These are the little guys that build the heavy things, like protons and neutrons. Then you've got the leptons. The most famous one in this family is the good old electron. And finally, you have the bosons. Now, these are a little different. They're the force carriers. They're the particles responsible for things like light and the forces that hold atoms together. Just stop and think about that for a second. It's mind-blowing. Every single thing in the universe is just a different combination of this handful of particles. It's so beautifully elegant. But, and this is a huge but, the way these particles behave is anything but simple. And this, my friends, is where our journey takes a very sharp, very weird turn. Because once you get down to this super tiny fundamental level, these things we call particles, they stop acting like anything we're used to. The normal rules just go right out the window. In our heads, right, we picture a particle, say an electron, as a tiny little billiard ball. It has a specific location, it follows a specific path. Simple. But the quantum world, it's not simple. It says that an electron isn't just a tiny ball, it can also act like a wave, all spread out over an area. This absolutely bizarre idea is called wave-particle duality, and it's a core concept of all quantum mechanics. It's not that an electron is sometimes a particle and sometimes a wave. No, it's somehow both, all at once. And the experiment that proves this is famous for just how strange it really is. It's the famous double-slit experiment. Okay, so imagine you shoot electrons one by one at a wall that has 2 little slits in it. On the other side, there's a detector. And sure enough, each electron hits the detector as a single little dot, like a tiny bullet. But, and here's where it gets crazy, after you shoot thousands of them, the pattern of dots that builds up looks like a wave pattern. The only way to get that pattern is if each single electron went through both slits at the same time, like a wave, interfered with itself, and then decided to land in one spot as a particle. It makes no logical sense, but it happens. Yeah, if your brain is starting to ache a little bit, that's totally normal. You're in good company, because this paradox forces us to ask some really, really deep questions about what reality even is. And just when you think it can't get any weirder, it does. The moment scientists try to peek, the moment they put a little detector by the slits to see which one the electron actually goes through, the wave pattern completely vanishes. The electrons start acting like simple billiard balls again, going through one slit or the other. Think about what that implies. This simple act of measuring, of looking at it, forces the electron to make a choice. It stops acting like a wave and just behaves like a boring old particle. It's like the universe knows we're watching, and it changes its behavior because of it. Our observation isn't just a passive thing, it actually helps create the reality we see. Which brings us to the final, mind-bending question. We started this whole thing with just a simple speck of dust dancing in a sunbeam, and we've ended up here. If the most fundamental bits of our universe exist in this weird, fuzzy cloud of all possibilities until the moment we look at them, then what is real when no one is looking? What is the universe doing when we turn our backs? And honestly, that's a question physicists are still scratching their heads over.